All right, so the thing is that it is a new room, and we're all playing with technology, as you can tell. That's fine. We usually, this is the oldest room, actually. Most of the talks used to be given in here. That room downstairs was constructed about 7 to 8 years ago, and it's been very useful for us as a laboratory, but it's certainly soulless to my feeling. It doesn't have any kind of connection with people. Somebody asked about the word quantum. Where does it come from? Quantum is a Latin. Latin means how much in Latin? Quantum, and so basically it's a word for a chunk of something. And so we'll see that a lot of quantum mechanics has to do with chunks, but a lot of it doesn't also. And in particular, I call this lecture Quanta and Waves, because we'll talk about waves and we'll talk about chunks. And what we'll really talk about, this is the most pathetic, I mean, is that pathetic? Okay, I'm going to use a stick. That is just pathetic. So what we're really going to talk about is the fact that quantum mechanics has to do with the fact that we can use multiple ways to describe reality, and that there's different perspectives on things, all of which are equally valid and which are valid at the same time, even though they don't seem to be possibly valid at the same time. So that kind of gets inside your head with the kind of logic problem. And this logic problem is something that people wrestled with for a long time, and I hope you will wrestle with it too. In fact, I hope it's always my goal that people will wake up screaming 6 weeks after the lecture in the middle of the night in a kind of cold sweat and say, "My God, quantum mechanics, I can't bear it." So let's go on into this world and see where we get. I have to do something else actually. Yeah, though I have actually got my reasons for not quite doing that. I have to get the second application. I have my reasons, believe me. So why quantum mechanics? So what was wrong with good old Newtonian mechanics? Probably you've all been learning mechanics. You're probably sick to death of the inclined plane, the Atwood machine, my personal favorite. I don't know who Atwood was. But anyway, the Atwood machine, which is really fun, the projectile motion, etc. More seriously, the orbits of the planets, the orbit and the things of that nature, basically the mechanics of the universe. And we use Newtonian mechanics all the time. Astronomers in particular are constantly filled up with it. You can discuss the entire dynamics of the sun, of the galaxy, etc., mostly with Newtonian mechanics. So what was wrong with that? Well, it wasn't designed for doing things very, very small. It was designed for doing things on a human scale. It's natural that people started off with their experiments sort of at a kitchen scale. If you think of what was done in the 1700s, 1800s, that's what they were, maybe big kitchen. So it was not designed for doing physics of the things that were very, 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 very small. And we're going to talk about how small is small, but it's pretty small. So what we'll do is survey the situation that led up to the quantum revolution. We'll ask what's all this stuff about particles and waves, because most people have heard a bit about that. In fact, sometimes I'm surprised at how much more about quantum mechanics that people in the room know than I know by using the prestigious internet to tell them everything they need to know. So, but if that happens, it happens. I don't care. You get another point. You can hear it many times and still not understand it, so it's not a problem. And is it spooky? Because there's always this question about the mystery of quantum mechanics. There's been some very, very bad movies made on this subject. Very bad. Although I have to say the thing in Spider-Man 3 where the Sandman is created, it probably should be like, we should show it in the atrium all the time.
Spider-Man 3. I love it.
That's a pretty good movie. So that's not one of the worst ones. So where were we in 1900? Does anyone care? I mean, you guys even know about 1900?
Like everything back then has already been like proven wrong. Or
no, that's absolutely not true. In fact, in 1900 they were in pretty darn good shape. They understood classical mechanics. I told you that. That was F equals ma, and it turns out dominates to this day the bulk of everything that is done by everybody In fact, including almost all fields of engineering. Thermodynamics they knew about, which was okay, definitely okay, and it hadn't changed hardly a lick since then. It's pretty much the same. Atomic theory, they knew about atoms. Most people believed in them. There were some physicists who still were holdouts, didn't believe in atoms for a long time, including one of Einstein's teachers. And they thought they had a complete understanding of electricity. And that was the thing that had just recently happened, and everyone was very, very excited about it. They had discovered the electromagnetic wave, and they discovered that light, as we see by, was connected to electricity. Now that seems not obvious, I have to say, at the very least, to start out. If you think about light and you think about electricity, there's no obvious connection between those things. This was a great triumph of the 1800s, was the discovery of the electromagnetic wave. This is just a picture out of one of my favorite textbooks, which shows an electromagnetic wave propagating in space. It has something called an electric field, which is nothing more than a vector that describes the force on a charged particle that transmits itself through space. Magnetic field describes the magnetic force on a particle. They're connected in an interesting way. The connection predicted the speed of light, and then there was prediction that there would be energy transport going this way that was related to those vectors. This was a huge thing, and it still remains to this day the focus of the entire telecommunications industry. Cell phones should be placed in their new positions. I assume we've all done that. So is it. Thank you. And that was good. So they thought they were in great shape. They knew that accelerated charges make electromagnetic waves. They know that if you take a charged particle and you shake it, the electron had been discovered. They actually knew about the first of the great elementary particles, the electron, by 1900. Very shortly thereafter, they discovered the proton, which makes up really your weight. You know, by the way, speaking of electric fields, I just mentioned to you, you are nothing but electric fields. If you take all of your matter and took away the electric force, and vanished all your matter down into, compressed it down into like nuclear size without the electric fields, it would occupy a space about a tenth of a millimeter by a tenth of a millimeter by a tenth of a millimeter. Right? So basically, you are electric, you're just big bags of electric. It's everything, all matter, it's nothing but big bags of electric fields, really, when you get right down to it. So it was a big triumph, and the accelerating charges do make electromagnetic waves. Radio had just been discovered. In 1901, radio signal was sent across the Atlantic Ocean. That was the first beginning of wireless communication, although they'd had telegraphs for 50 years already. And the radio transmitter is an example of something that will make this happen. It's a fundamental prediction of classical physics. Now we see if the first animation works. We hope it does. We think it will. Hold our breath. Blip. Okay, so this is a really great animation. You can set the speed of light to be infinite, which I'll do first off, and show you what would happen if it were. You move your charge around. Here's this oscillating charge in the center, and it'll move around. It moves around, and since the speed of light is infinite, the lines of force coming out of that charged particle just go up and down together with it. So it means if you're out here somewhere, you're getting force on you, and this thing's moving up and down, and you know what's required. Great. And it stops. Hello? Now we go again. Somebody told me to turn off the wireless LAN. I suppose we did. But more interestingly, it turns out the speed of light is not infinite, and what happens when these things actually go is that you get these kinks in the lines of force, which transmit their way out. And out here, he doesn't know about anything's happened yet. Okay, now this person sees a change in the line of force. And so what we see is something's happening here. Now, what do you think is happening? Yeah, the interesting thing from our point of view is that this thing is shooting something out of itself. It can't do that without losing energy. I mean, these things are carrying energy. They have pressure, actually. And it means that these spidery objects going out of here have pressure, and this thing is losing energy. You've got to keep feeding that thing. So if you turn off the power connection to a radio station, no more radio. It won't keep going by itself. It requires a lot of electrical energy going in to make that happen. And that turns out to be important and was one of the first clues that something was messed up in the classical worldview. Okay, the other thing they knew about waves, which is related to the other thing I'm going to talk about, this, which is this equality of descriptions of things, is they knew about polarization. They knew about this a long time earlier, in fact. You probably have all heard of it. How many people have discussed polarization in class at all? About half, okay. Well, I'll talk about it. Anyway, the electromagnetic wave I showed you goes this way. It had an electric field that is going like this. You can also get one that has an electric field that's going like this. And those two waves are referred to as being polarized vertically or polarized horizontally. And it's discovered that there are materials that will only let one of the kinds through and not the other kind through. The typical sunglasses that you buy, or the Polaroid sunglasses, have this effect. So if you take two pairs of Polaroid sunglasses and you rotate them like that, nothing comes out, because you made it so that only this can go through, and then you turn it so that only this can go through, but there's nothing left. So this is a diagram of that showing polarized light going in. Transmission is oriented this way. You have one that's turned like this. Transmission is oriented this way. And that was interpreted by, this comes from a site called Hydrophysics, which is a lot of fun, by the way, if you ever get a chance to go there. And this is interpreted as direction of the oscillating electric field in the wave, the polarization. Now, in quantum mechanics, we'll reinterpret what that means. But but at that time, it was a good thing. The third polarizer, however, plays with the vector nature of the wave and really makes things start to be interesting. Suppose I take one and put it in the middle at 45 degrees to the other. So now I let only the vertical component through, but now I set up something that will only let this component through. What happens? Well, only that component comes through, but now this vector that came through has a component this way, whereas this one didn't. So now, if I put a cross polarizer like that, something comes through. About 25% of the total comes through. So we actually changed the situation by putting this middle one in here. We actually made it so that something that was black, a black dot, is now suddenly letting light through. So that result, and it's interpreted in classical mechanics as resolution of the electric field into vector components. So here's a question that was at the interface of electromagnetic and atomic theory. Does this description still work at scales of very small atoms, because the atoms are really, really tiny? We have every chair people are sitting on the floor. Are you comfortable? As long as you're comfortable, because there's still some chairs up here. I don't want anybody to, have to go to medical. So does this description still work at scales of very small atoms and very weak waves, or not? And the question is, or does it have to be changed in some way? And it picks out a component, and what does that mean when you're talking very small? Now, so I put this up as an introduction because we're going to come back to it, okay, in the second half. The wave nature of light was very well known. It was known before any of the invention of radio or any of the electromagnetic waves or anything. It was known in the 1820s. There was a guy named Young who figured it out. This is his original picture that he showed when he gave a talk like this in 1820, or maybe it's 1803. Yeah, 1803, really a long time ago. Can you imagine he made that picture with like a pen and ink? I guess it was like and what you can see from the picture is that you take a wave, which is a big distributed thing, goes up and down like this, and it has a wave length, which is the distance between the peaks, and it has a frequency, which is how long it takes for it to go up and down. And this wave, and you put it through two very narrow slits, and what happens is, as it hits that, little waves get generated at each of these holes, and as they go out, two of these waves can be added to one another. So you can add waves on top of one another. It's a very important concept we'll come back to in a minute. It's called superposition. And if one is up and the other one is down, they cancel. So they actually add up and cancel one another. That's a very non-trivial physical phenomenon. I mean, there's no reason to think, if I take two marbles and throw them at each other, normally they don't add up to be zero marbles, right? But waves can do this, and they go up and down, and you can put a screen back here and look and see the pattern you get out, and you get a pattern of bright, dark, bright, dark, bright, dark, which is where the things have added up or subtracted. So that's a characteristic spread out pattern, I call it, of light and dark, that you get from waves. It's known as the interference pattern, and this is the two-slit interference experiment. It's in a lot of laboratories. Some of your schools might even have a chance to do this experiment because you can do it very beautifully now with a laser. It was always a little hard to get the right kind of light before, but now you can. So the early tests of the new atomic regime, so they knew about that. So just a second. So they had light being this, and everything was going great with light being a wave, except for something that suddenly didn't work. And this was the photoelectric effect. Now, the photoelectric effect was considered really cool at the time. You put a piece of metal down and you shine a light on it, and electricity comes out. And so that is really cool, extremely useful, and still, of course, very, very important to us. The light on metal produces outgoing electrons. As I said, the electron had been discovered in 1897, the first of the elementary particles to be discovered. The first idea really helped with the confirmation of the idea that everything was actually atomic in nature. Thermodynamics and so on, Newtonian mechanics, they don't care if things are atomic or just big solid things, but now we're starting to discover things are. And they did the experiment, and it was all wrong for an electromagnetic wave. With a wave, if you think of a wave, the energy comes in, and then more comes in, and you just sort of add up. Think of the sand on a beach. You bring sand in, you bring some more sand in, you bring some more sand in. You gradually pile the sand on a beach higher and higher, which means that you have a hill which has potential energy. You've actually added energy to that beach as you bring things in. So energy is brought in gradually by waves. And there should be a time lag after you turn that light on as the energy builds up, and eventually there'd be enough energy to push the electron out. Okay? Does that make sense? That you turn this thing on and you wait, and then gradually it would get hotter somehow, and then the electron would come out. That was not what happened. Turn the light on, bang, immediately the electrons come out. Even more bizarre, you had a different color light and it stopped. The color, where did that come from? Right? They knew what color was. Color was that it had something to do with the frequency of the light, because you could figure that out by using prisms like Newton did and doing two-slit experiments like Young did. So they knew that. But what's it got to do with this? Nothing. So this picture shows, I love this picture. It shows you the infrared light hits this thing, no particles come out. The red light hits it, no particles come out. A blue light hits it, all of a sudden particles come out. An ultraviolet light hits it, all of a sudden faster particles come out. Okay, we have a mess on our hands. And I would say that we were really lucky in that period to have some brilliant people like Dr. Einstein, who, besides inventing relativity, also invented what's called the explanation of this, the photoelectric effect. In the same year that he was doing relativity, he was doing this. He was also doing another explanation of the Brownian motion, and he was working a full-time job and had two little kids. So, imagine that was he was a smart guy. And he said light comes in little particles called photons. Now, the idea of light being a stream of particles is ancient. It goes back to the ancient Greeks, as a matter of fact, and Newton believed it very strongly. He wrote a book called Optics, in which light was a stream of particles, but it had been pretty much trashed by all this wave business that was going on and that I was talking about. That was, because you knew now it was a distributed wave, electromagnetic wave. In fact, we figured everything out, right? It was 1900. In fact, there were people who said we figured everything out. That's it, no more. I'm sorry. They were a little bit wrong. Each packet, so he said this light comes in little packets. Now, this is a typical Einstein thing. He said, well, it can't be like that, but it is anyway, and be right. If you can do that, I recommend a career in physics, really. So each packet is absorbed individually, and the energy of the packets, he said, depends on the frequency of the wave. Huh? As energy equals this constant, h, which they do from another experiment, times the frequency, which we're using the Greek letter there. That's the Greek letter nu. You may not have seen it before, but we use it for the frequency. I would say this appears to make no sense at all. You have now reached a state of linguistic confusion which is logically seems to be completely inconsistent. I mean, it explains all the facts, however. It won the Nobel Prize and it changed the world. So it made no sense at all. People had very great questions about whether this could be used, so it didn't make any sense here. We have now a wave with frequency, which is little chunks. I'm sorry, but that doesn't go. It's as if a wave at the beach suddenly resolved itself into nothing but a large but individual surfer, coming down riding on nothing. Yeah. Or one surfer, even worse. The silver surfer. No. So I like to talk about real-world applications. This is the first real-world application that I knew of one of the photoelectric effect, a very important one for us, the photomultiplier tube. Every particle physics experiment that you will be toured to see around here has 1 million of these in it. In sensitive applications, you can detect individual photons coming in one by one, bang, bang, bang. You can actually see the individual pulses. The light comes in, it goes through a window, it hits a piece of metal, electron comes out, hits a piece of metal, makes a bunch more electrons come out. They gradually amplify, and then you get enough at the end to where you can measure it. My personal fun fact connected with this thing is that the first application was in the first sound that they put in movies. Movies were silent until the 30s, 1930s that is, and when they eventually made them work, they worked by putting a trace on the film that was dark or light on the side where you can't see it projected on the screen. And they put shine a light through there and get a stronger or weaker light, which would go through into one of these and make a signal, which they would put into a audio system, and then you could hear something. So that was actually cool. They were using the most recent physics possible to do movies. So every time, it turns out today one of the hot applications is computer graphics. The next problem was sort of something that the theorists didn't like very much, and this time, usually they're wrong, but this time it turned out they were right. Like our radio station, they started thinking about how are atoms put together. Now the original idea was that atoms were so-called pizza-type atoms, where the electrons were like the pepperonis in a pizza. You imagine that they're just sort of sitting and they're distributed. But actually, they had a reason for that. They didn't like the idea that electrons would circulate around the central nucleus in the atom, which was okay until somebody named Rutherford discovered that there was a nucleus to the atom, a very small thing, much smaller than the atom itself. That was an experimental discovery in 1911. Big problem now because the atom size was roughly known. I just told you that the atom size is 3 orders of magnitude bigger than the nuclear size, so that's why you're all electric field. So the nucleus of the atom was discovered in 1911 by Rutherford, and so no matter should exist at all. Basically what should happen is, this is accelerated, right? In circular motion, we have an acceleration which pulls towards the center, the centripetal force, which is pulling towards the center. If you don't have acceleration, things travel in straight lines. So this is accelerated. It should give off a lot of electromagnetic radiation. In fact, in the classical regime, when we build an electron accelerator, that does give off an incredible amount of radiation. Usually in X-rays, it's called synchrotron radiation. It's used exhaustively for study of materials today, and so on. So it's true. Electrons going in circles give off radiation. However, in atoms, somehow they don't. Because if they do, in an accelerator, you keep pumping power into it. But in an atom, there is no power. So this thing should just spiral and spiral and spiral down to the center and annihilate, and there would be no matter, nothing. So there was no. So now we have the kind of problem that really bothers physicists, namely that there's no reason for there to be any matter at all. If you think we've solved that problem, by the way. So Niels Bohr discovered how the quantum theory could be applied to the atom. And he discovered it as soon as the nucleus was discovered. Inspired guesswork, I would say. He made a picture of the atom that consisted of the nucleus and atoms going around in circles or other shapes, but we'll use circles for now. And his statement was, well, they go around in circles, but they don't radiate. I mean, you know, you say they radiate, I say they don't radiate. That's it. There's a German word for this called Ansatz, which means it basically means you just throw something down the table and say that's it. You know, and this is what it is. There were several of them. Einstein used this all the time. He said, speed of light is constant in all phrases. Bang, that's it. You know, check it out. You know, this thing is a particle and a wave. Up, that, check it out. You know, these things go around in circles and they don't radiate. Well, okay, the orbits are stable, said Bohr, unless they jump between different levels. That says that we should see photons coming out with specific frequencies. You do. If you look at the frequency of radiation emitted by a hot atom, you'll see lines instead of a broad spectrum as a function of the frequency of the radiation coming out. You see these very sharp lines. That's called spectroscopy. And the radii, he said, are set by this formula, which he made up, which is the radius is a number, 1, 2, 3, 4, 5, times this famous Planck's constant here, divided by 2 pi times the momentum. And momentum is set by the circular motion equation. So there's no continuous radiation. And this determines most of atomic physics, so it's probably worth an animation. I also really like this animation. So we'll give it, boom, there comes a, of this. You have your electron going around, and I'm going to put in a high energy photon coming in. Boom! There, so the thing jumps up, now it decays, and little photons come off. Here comes another photon. Oh, there it comes. Wow, it seems to always go to the same place. Well, that's not what happens in reality. In reality, you can't define the place that well. But anyway, so you get the idea, and most of you have probably heard of this, because it's very popular in chemistry courses. It's discussed extensively in popular works. And it's the Bohr model of the electron, of the atom. It also makes no sense at all. So now we have things that make no sense at all but seem to work. And that was the situation we were in let's say, up to about 1920. Okay, there's a practical application of the Bohr, besides all the chemistry you know, which I like very much, which is the atomic clock. This picture looks like it was written in 1950. In fact, this is a function of the fact that I got it by emailing myself something from the Xerox machine. This picture was in the Physics Today of this month, in an article by a guy named Camparo on the atomic clock. And atomic clocks are very important. They're the way we keep time now. There's an atomic clock on every GPS satellite. It turns out that GPS satellites would drift with respect to the time on the ground by quite a bit based on relativity, the fact that they're at a different gravitational potential than down on the Earth. They would drift by 5 microseconds every 3 hours, which is a lot in the short time world. Microseconds are long in particle physics or in any kind of atomic physics, actually. So they need something a lot better to compare with, and they compare with these atomic clocks. An atomic clock works like this. You shine a light through a cavity full of some gas, in this case it's something called rubidium, and it makes one of these quantum hops if you have the right frequency. So you adjust the frequency of the light until you get until suddenly the intensity coming out goes down because you've absorbed some of the energy out of that beam. When that happens, you feed that back into your radio system. Your clock system is controlling your clock, and change the frequency that's controlling the clock by a little bit, which also changes the light frequency, and you put that into a feedback connection, and it's this hop between these two levels that determines the frequency, which is frequency then tells you exactly how to translate that into time. You use the speed of light, which is very well known, and you can turn the frequency into time. So hopping Bohr level sucks power out of this light beam. So and there's one of these on every GPS satellite. And there are many other applications to atomic clocks. They're one of the reasons we have such precision knowledge of the world today. Right, things only continue to get worse. As I said, they were in a situation of complete contradiction. Nobody understood anything about what to do, and it was what's called the old quantum theory, which basically looks like, to me, books of black magic. You open up these books, and they have like, then you do this, and you do that, then you make this guess, and you make that guess. So, a Frenchman came along in 1923. His name is Louis de Broglie. Louis, in his PhD thesis, asked the following question. He said, from the reasoning from the photoelectric effect that we talked about before, he said we should ask the question, if photons have a twofold nature, which we just said they did, they were waves and particles at the same time, why not apply the same principle to electrons? Why not say that electrons might also have a twofold nature? That we think they're particles, but maybe they're also waves, he said. So he made an assumption that, reasoning from the idea that in a photon, energy is equal to the h times the frequency, he said in an electron, momentum is h over the wavelength. This is the same basic equation. And 1 over the wavelength is like the frequency, so you should be aware that these equations are very, very similar to one another. And he wrote that down and said we should test this conjecture and see if it makes any sense, and sent it in as a PhD thesis, which was immediately rejected. Then he said, no, there's no way you can graduate with that. That's just stupid. That was rejected. He got upset about it. He wrote a letter to Einstein in which he said, I don't really think this is that bad. What do you think? Einstein wrote back to the authorities at the university and said, this is the most brilliant PhD thesis you've ever seen in your life. If you don't graduate this, you're a complete idiot. And then I'm out. So that's the way the cookie crumbles, but we were fortunate that it actually worked in this case. Okay, so Louis said particles were waves, which means that we can have a two-slit experiment for particles. Now, for classical particles, the two-slit experiment looks different than it does for waves. I already talked to you a little bit. These are pictures from Feynman. I told you a little bit about what happens with waves. You go in here, you get the two sets of waves coming out, and they kind of add up to this thing with light and dark peaks at the end, up and down, up and down. If you do that with regular particles, like a gun that shoots bullets or something, and stuff's going through one slit will make a distribution that looks like that. It kind of bounces around a little at the slit so it doesn't all come out straight to the center, but you get a distribution that comes out and looks like that. And the other slit, you get a distribution that looks like that. And when you finish, you add up the two distributions and you get something that looks like that. So that looks completely different from this. So particles and waves have totally different behavior under a two-slit experiment, for which we really need that information. So this is the particles, and there they go. They're going in, thump, thump, thump. Oh, that one went straight through. Oh boy, hot dog. This one bounced. Yeah. This somebody mentioned that this looks like a very old computer game. Okay, but now we have waves, and they're going to behave differently. Yeah, okay. They're coming all at once for one thing, and they make this pattern of dots and dashes. Particles make individual clicks as they hit the thing. The way they used to do these experiments is they had screens with phosphors on them, and they put a little microscope on there and they count the little dots. No computers in those days. It was tough. Between drinking tea and sherry, you had to sit there and count particles. It seems like a very strange idea that electrons would have a wave nature. So, but it was verified by Davison and Germer, who were working for the phone company, which used to be a massive research enterprise in the United States and was dismantled in the 80s. They were working for the phone company, and they put together an experiment. I got this out of a German book. So the Elektronenkanone shoots down to the nickel crystal, which then goes to the detector. And they shot these. They shot electrons at a crystal and bounced them out. And you could, if you have a crystal that bounces something, or for light also, this serves almost the same idea as the two-slit experiment, except that it's reflecting. And they got this pattern as a function of energy. It came out, went out, came back down in. Typical diffraction pattern, but with electrons. Proved positive, certain 100%, that the electron had a wave nature. This also turns out to have big money involved in it in real life, for a real life application. This material is called a methane hydrate. It consists of atoms of methane, which is basically natural gas, with water molecules stuck in between like that. It's formed under great pressure at the bottom of the ocean. And some people say it's a possible fuel source. You could mine that stuff and bring it up to the surface. Some people say it's a place you could put carbon dioxide by pumping it down until it's in the, making a similar hydrate at the bottom of the ocean. But people don't know a whole lot about these things. And the way they study it, this is a picture from a neutron source, a high energy neutron source in Tennessee. And the way they study it is by putting by making a source of neutrons and using their wave nature. So here's the neutrons coming along, and they're behaving like waves, and they bounce off this material, and you analyze the diffraction pattern, that thing that I showed you before, in much more complex in 3 dimensions and so on, somewhat like an MRI or other tomography, and you analyze that, study the diffraction, and you can understand the structure of this thing under various circumstances. So we use these particles as waves to do this all the time. All right, so now once you have these waves, they can do some cool things. They can become standing waves. They can form a standing wave pattern. This is like the notes in an organ pipe. This is the lowest note in the organ pipe. It goes up like this. If you could see this in time, this would be going like this. And this one will be going. This one going. Okay. So you see that it has more nodes in it, and this one has 1 node in it. The node is where it goes through 0. It says no nodes in it. Higher frequency, it's just like musical notes, as I say, in a flute or a trombone. And the higher frequencies mean higher energy from the quantum principle E equals h nu. This is what we call a particle in a box, but it won't escape your notice that this looks a lot like what we did with the Bohr atom. There are specific energies connected with specific frequencies. And to go between here and here, you have to emit a photon on a specific frequency. So this is a model, particle in a box. It goes up to infinity on the sides. But it's very similar to the Bohr level in the atoms. In fact, if you wrap it in a circle, take a proton and wrap these waves around themselves in a circle, if you do just the right number of times, they'll add up on top of each other as they go around. If you do it the wrong number of times, they'll miss, and eventually you'll get nothing. So when wrapped in a circle, see this one misses here? The idea is that this will eventually go around and average out to 0. When wrapped in a circle, the de Broglie waves naturally close on themselves. So if you put those simple equations we talked about, which I don't expect you to remember, but if you put those equations into Bohr's radii theory, formula, which we took from his model, you get this. 2 pi times the radius, that's the distance around, is equal to n times the wavelength. So it just means that if you have n wavelengths, 1, 2, 3, 4, 5, 6 wavelengths in this case, going around, and they go around just right to match up, then you get Bohr's thing that he made up. So that says that the waves actually have something to do with reality. These waves have enabled us to understand what's the physical origin of this criterion that Bohr made up to fit the data, basically, of all the spectroscopy. And somebody made a nice picture of an atom that consists of these different waves going around like that, straightened out, and you wrap them around here like this. Now this is in 2 dimensions instead of the 3 dimensions, but it really doesn't make that much difference, it turns out, for this particular application. The Bohr orbits are the closed waves that we see. More complicated, you have a 3D calculation that gives you all the stuff you studied in chemistry. Everybody studied S, P, D, and so on in chemistry. Here they are. And once again, familiar to you. They're determined by the wave function. The wave function is this thing psi. It's nothing but that, the height of this wave that's associated with the particle going around. So it's not a mysterious thing. And there's a way to put that together using to form a probability density plot. Now this is where it starts. We got to get into the second part of the discussion, the different ways of thinking about particles. They show you where you're likely to find the electron. The electron's now a wave, so it doesn't have a location. That should mess up your head. The electron's now a wave, so it doesn't have a location. Its waves are all over the place. They're distributed by nature. They don't have locations. Particles have locations. Yet, when we use a two-slit experiment, we get a wave pattern for things that arrive in chunks. So it's behaving like a wave and a particle at the same time, depending on which aspect of the behavior you want to look at. So these are probability density plots. They show you where you're likely to find the electron. And as I say, the wave nature has smeared out our knowledge of the position. So the fact that you know, in fact, what the energy is here, or the momentum of these things going around, as we did in a Bohr orbit, we knew the momentum. We had to set that. That goes back there. You see that the momentum has to go into the two equations to give us this condition on closing the waves. We've lost knowledge of the position. We don't know where it is. These are complementary descriptions. It's two ways of looking at the same phenomenon. Depending on what question you want to ask, what experiment you want to set up, you can either understand a lot about exactly what the momentum of a particle is, which is very useful if you want to study the radiation coming out and those lines, the spectroscopic lines we talked about, or chemistry, why things bond together, or most stuff. Or you can ask yourself, where is the electron? But then you won't know what its momentum is, because they are complementary. So I just finish up this half with the two-slit experiment as a probability. Well, actually, you know what? I'm going to put this up and show you the video, and then we'll take a brief break and some questions, and then come back. Okay? For electrons, when we do the two, so just to make a summary, for electrons, when we do the two-slit experiment, the wave nature appears. However, each electron gets there as a lump. It doesn't travel like a lump, but it gets there as a lump. We say we don't know what path it took. Nature, the wave nature means that this thing has sampled both paths. So you get an electron here, you say, did it come this way through this hole, or did it come through this hole? Well, we say it goes through both holes. The electron is a wave at this point. It's going through both holes at the same time. You have to do that in order to reproduce the pattern of bright and dark that you see at the end. This should really be messing with your head at this point. I mean, you guys should be pretty uncomfortable.
How does the electron go through both holes at the same time?
Well, I'll show you. The prestigious internet will show you the answer. So this is the number of electrons versus position on the screen. There they are, building up. They come in as lumps. I can make this go faster.
This is really small.
It's even more
Like
fun.
really slow touching.
And they're building up. Each one gets there as an individual thing. And we say, okay, we know, we'll just measure, we'll just histogram. This is called a histogram of where they land. By each one lands at this given point, we put a tick mark in there. And we start to get something strange. We start to get a pattern of light and dark bands. The only way that I know of that you can get a pattern of light and dark bands is by interference of a wave with itself. The only way it has to go through both, which requires the presence of something going through both holes at the same time. If you actually cover up one of the holes, or worse, if you put something at one of the holes that tells you which one it went through, something that flashes, a light bulb that flashes when the electron goes through the hole. So you put on the top hole a light that flashes.
So it acts weird when no one's looking, but when you're watching.
If you watch it, if you put that light on the hole and make this picture, this pattern will disappear.
So it doesn't like to be watched.
So it depends on when and where you are watching. If you are making it observable, you've done an experiment at the other end of the hole, and you get a different result. So it behaves like a wave during the period when it's not being when you're not observing, and when you're observing, it typically behaves like a particle. Okay. So I'm going to stop there, and we'll come back to that after the break. Talk about a little more questions, though, first before. Questions?